Hello everyone, this is Rahman Muhammad Abdul, and this is my project for CAP 6415 titled Probing SOTA Models with Hard Examples. The goal of this project is to analyze where a state-of-the-art model fails on CIFAR-10 dataset and to understand those failures through hard examples, extraction, and GradCam visual explanations. The idea is simple. Instead of only reporting accuracy, I dig deeper into where the model is misclassifying or uncertain, and I use visualization techniques to understand why. So let me walk you through the repository structure. So in the script section, I've got train.py, which fine-tunes ResNet 50 on CIFAR 10 using Google Colab T4 GPU. Evaluate.py computes accuracy, confusion matrix, prediction CSV. Hardexamples.py extracts misclassified and low confidence samples. Gradcam.py generates Gradcam visualizations for selected samples. Baseline.knn.py generates simple KNN based baseline for comparison. Data.py generates CIFAR10 data loaders and transforms. And utils.py helps function like checkpoint, loading, accuracy, etc. And we've got models. So in the model, we've got ResNet 50 fine-tuned path, which is a basically final trained model checkpoint, which we use in further evaluations. And we've got results here, which are basically we got test predictions, fine-tuned CSV, confusion matrix, baseline results, and we will see in the further video. And we've got GradCam outputs as well. So basically, we will have two outputs. One will be misclassified and there will be low conf. So the misclassified is nothing but heat maps for misclassification examples, and the other one will be heat maps for low confidence examples. And after that, I've got weak logs from 1 to 5. So that's the full structure used to keep the project clean, modular, and reproducible. For training, I used Google Colab because my local GPU MX450 is not strong enough for deep learning workloads. In Colab, I selected the T4 GPU accelerator, which significantly speeds up training. The training script I wrote is train.py, located inside the scripts folder. So let's just go to the train.py. So here you go, the train.py. The model I fine-tuned is ResNet 50, a popular deep convolutional neural network pre-trained on ImageNet. Since CIFAR10 contains much smaller images, 32 by 32, ResNet 50 is very powerful for this task. The idea was to take this pre-trained model, replace the final classification layer with a 10 class output, and fine-tune it for a few epochs. So I did about 3 epochs. So this is the train.py script. Starts by importing OS, time, pandas, torch vision. So the script applies normalization that matches the dataset statistics. Next, the script loads the ResNet 50 architecture with pre-trained weights. The final fully connected layer is replaced with a new linear layer that outputs string classes for clear CIFAR10. So I use the Adam optimizer with a learning rate of 1e4. This is a common learning rate when fine-tuning pre-trained models because it updates the weights gently instead of drastically overwriting them. And the batch size which I used here is so the batch size which I used here is 64, which is a good fit for D4 GPU memory. The loss function is cross entropy, standard for image classification. So inside the main training loop, each batch is passed to the model and gradients are computed using backpropagation. The model parameters are updated at every batch. I trained for 3 epochs, as I said, which takes about 25 to 30 minutes on a T4 GPU. I don't know why, but so during each epoch, the script tracks loss accuracy and progress using progress bars. So when the training completes, the final fine-tuned model checkpoint is saved into the models directory as ResNet50 fine-tune.path PTH. So this checkpoint is loaded later by evaluation and grad scripts. The training scripts also writes a CSV log file into the results folder named trainlogs.csv. So which I will show you, which contains the loss and accuracy for each epoch. So if we can go to the results section. So this is the train log, what I got from here. So basically here the accuracy is somewhere around 90%, which I got. So it is expected for a lightly fine-tuned ResNet 50 on CIFAR 10 with just a few epochs. So this accuracy is later verified using evaluate.py, which I will show you in the further video. So let me just run the code in Colab. So let's open Colab. And before we begin, we have to change the runtime to T4 GPU. And then let's copy our GitHub URL. Let's run it. It will take few seconds. And let's give command. And then let's install all the requirements. So it's gonna take few seconds. So yeah, it's done. So now let's start with the evaluate.py. So let's just run evaluate.py. That would be partners. Let's just run this. Yeah, it's running now. It says using device. Pura. So yeah, we're almost there. So this evaluation script computes test accuracy, confusion matrix, and generate a full prediction CSV file. So the key outputs are test predictions fine-tuned CSV and confusion matrix fine-tuned CSV, as I said. So The overall accuracy will be 95.94 percentage, and classes with highest confusion, uh, cat versus dog, airplane, truck. So these are saved in results folder, computer matrix find, test predictions find in CSV. So let's do one more here. So that would be extracting hard examples. So let's run it. So the hard examples.py script selects two categories. So one will be misclassified samples, that is model prediction through label, and the low confidence samples, that will be soft max probability 0.40, less than 0.40. So, so in the misclassified samples, this is having about 406 samples, like 406 images, and the low confidence will be having 21 images. So low confidence predictions may not be wrong, but they indicate ambiguity. These cases highlight uncertainty in the model. So let me just do one more thing. Let's do radcam.py. So basically, it will analyze the both CSVs from hard examples or py and generate images. So let's just do it. Everything. Let's just run it. So basically, it is going to download all the images from those two CSVs. So Platform highlights the regions and words focused on when predicting. So here are examples from this classified set. So it has taken up all those images for us. So if you go to let's go to the file once, just check what kind of images it generates. So basically, these are the kind of images which are generated by background.py. So this is having some kind of heat map focuses on background. So leads to wrong classification. The model confuses similar classes due to overlapping features. And these are the two images which I took from out of 21 for low confidence example visualization. So here the heat map is diffused and weak. So these visualizations help diagnose why model fails. So So now the future improvements part I'm going to discuss. So one would be CIFAR 10 is too small, 32 by 32 images. But for representation, I have enhanced the size of the images, especially for the readme file. So the Brad explains attention, but at such low resolution, heat maps are limited. The conclusions are made so that a higher resolution dataset would provide clear insights. And the second would be limited training time. So I trained ResNet 50 only for 3 walks due to time constraints, and that took me around 30 minutes. So with longer training or better hyperparameters or with better GPUs, accuracy would increase and misclassification would drop. And the third one would be no model comparison yet. This project only analyzed ResNet 50. In future work, I could compare multiple architectures like efficient net to see if hard examples differ across models. So the fourth one would be no automated hard example mining. So right now, hard examples are extracted once a more advanced version to retrain the model specifically on hard examples to improve performance. So if I can summarize the future improvements, that would be train longer or tune hyperparameters, use advanced augmentation like cut mix, use high resolution data sets. So this concludes my project demo. I demonstrated the repository structure, training pipeline, evaluation metrics, hard examples, extraction, platform visualization. Uh, Thank you so much for watching.